I can't really do the class without being able to draw. And I'm sure as hell not going to use the Zoom whiteboard and try to draw structures with a mouse, because that's not going to happen. I'm going to throw slides in here just for the sake of the integrity of the YouTube video that will exist off of this. But you can just follow along with the slides. The slides are really an outline for me, so I don't forget anything. Pretty much everything that you need, I'm going to draw, right? So the slides are there to just kind of be like a backstop for me, but I will throw them up. So we're going to start with what is organic chemistry. All right. So big picture, organic chemistry is a study of reactions and properties of molecules that contain carbon. That is it at its simplest thing. If it has carbon in it, we claim it. It's us. All right. So the field began in 1828 when Friedrich Wohler, he's German, they don't get W's, conducted the first organic reaction. And of course, there's a typo, and I can't fix it because it's a screenshot. So the first organic reaction was taking ammonium isocyanate and so if you ever see a little triangle above or below an arrow, that is our, we're too lazy to write the word heat, so we just draw a triangle. You're going to see all my notifications, but I did make it so you can't see what they are. Baby steps. And that made urea. So, up until this reaction, right, the idea was that if a molecule was made by a living thing, it could only be made by a living thing. That you had to use a life process, a biological process to make the molecule. You couldn't make it some other way, right? So when this reaction was done, it showed, hey, no, we can make organic molecules, molecules that come from nature and from life in a lab. We don't need to make it using an actual biological process, right? This was like peak science when, you know, the idea was that if you went and kicked a log in the woods and a snake came out, that logs in the woods made snakes. That's where we were in science, right? It seems pretty dumb now, but that's what we had. All right. So why does organic chemistry matter? Why is it important? All right. For most of you, the reason organic chemistry matters is because on your program evaluation, it says Chem 331. And you're here because your advisor was like, do you want to graduate? And you were like, yes. They're like, okay, you have to take this class, right? So I'm going to try to prove to you that there are like other reasons that it matters, right? It's the chemistry of life. Basically, any process your body does is an organic reaction on some level. So basically, all biology is organic chemistry in a cell, in aqueous solvent. That's it. So all your biology that you're learning is just this class. But you just go back like one level and you're like, yo, I need to be able to draw a square interacting with like a green thing, and that's biology, right? What that interaction is actually chemistry, right? Right? Most of the drugs in the world, both the ones you take at Tongies and the ones you take when you're sick, are organic molecules, like with very few exceptions. There are some big biologics that, you know, like insulin, that's an organic molecule, it's just really big. But most things are small organic molecules that have a molecular weight under like 500. Most of the energy in the world comes in the form of organic molecules like octane. We run on dead dinosaurs, a non-renewable resource, because first we'd have to have dinosaurs to let them die again. So, and then carbon as an atom is unique in how it behaves, right? In Gen Chem, you learned about atoms that either gave away all their electrons and became positively charged, or took electrons and became negative. So a lot of inorganic molecules come down to the positive thing hangs out with the negative thing, right? But since carbon is able to readily share electrons, it doesn't become positive or negative for the most part, right? It allows carbon to be the backbone for a more diverse set of structures. So you're able to build a whole bunch of different molecules using carbon as a backbone. All right, so chemistry is also, I think, all about reactions. I think that is kind of what chemistry is about. It's about changing matter into something else, right? So I look at organic as being no different, right? The goal is to take something that is cheap and readily available and not complicated and turn it into something that's more complicated and of higher value, right? So you've all seen this, but, right? So just remember that starting materials are going to be on the left side of your arrow. Then you're going to have some sort of reagents or conditions, and then you're going to make some sort of product, right? And that's basically the general gist of how every reaction is going to be written out. So going back to like cheap stuff to expensive stuff, or to expensive stuff or not complicated to complicated. So this thing is called thiophene, this 5-membered ring. And when I was in graduate school, my project was to, as he forgets what he did with his 20s, there we go, was to take that molecule, move that, and you don't have to draw this. This is more just a little history lesson. And make this. So this is thiophene. This is basically waste from the oil and gas industry. And this was an anti-malarial molecule that made it into animal testing with the military. This was it 20 steps? And it took my best years. Basically age 22 to 24 to 28. I hear those are good years. I wouldn't know. I was inside a lot, right? So, right, this is something cheap that you can just buy like the barrel full. And this is something that inhibits the progression of malaria. And we looked at for a few other things. So it's just, organic is taking something cheap and useless and turning it into like a drug. Again, a good drug. All right, so we're going to hop right in here. We're going to start talking about hydrocarbons. And hydrocarbons are the simplest type of organic molecule. As the name implies, they only contain hydrogens and carbons. Right? So, and they only have single bonds. So every carbon is bonded just once to every other atom in the family. So here we go. Let me change colors here. The question here was if the slides were going to be put on Moodle. And the answer is the slides are already all on Moodle. They are in course content. You can just go get them now. They are already there. Every slide that I have is already on Moodle for the entire semester. It's already loaded up. If you go under course content in Moodle, there should be a thing that just says like slides. All the slides are there. I know this is not the ideal way to do the slides. I usually like have them projected in the room, but I don't know. Pandemic. That's just gonna be my out. But yeah, they're all up. Right? So you have to do all of these. I'm just putting that out there now. Here we go. It's going to take a couple slides. And hopefully my handwriting gets better on my iPad as it goes. I really hope it does. A whole spring didn't super help, but... So, if you just have one carbon with 4 hydrogens attached to it, that's methane. I'm going to give you the kind of the smaller structure here. Right, we could just write that as CH4. The question here was if we had to write all this down. I think that came from the fact I said, don't write down the big molecule I drew earlier. But yes, you have to write stuff down. If it goes on the little whiteboard, it should be in your notes. Other than my, like, YouTube notifications. But yeah, anything I draw, you need to have in your notes. As a general rule, like I said, the slides are great, but what I draw is going to be the bulk of the course. Oh, hey, there's a whole nother page of people. Who is Loki holding Mjolnir and Captain America's shield? Because you're my hero. Thank you, Rachel. You're my hero. All right. So next, we've got 2 carbons. This is ethane. And again, we're going to work on board management, I swear. And that is C2H6. He redrew the 6. It was just as bad. All right. Going to go over a slide. Oh, as a general rule, this applies in class and I guess online. If I go too fast, make some sort of noise. If it sounds like stop or go back, that's better. But if you're just like, I'll stop. Sure. No problem. Cool. 3 carbons. This is propane. And this is C3H8. Next up is going to be 4 carbons. See, that is, hey, old man, you can't draw. And I understand, I can't. Yes, there is. There's a hydrogen on all of these. If you can't ever read my handwriting, this applies again online and in person. Just say something. I've been doing this for a decade now, and my handwriting still sucks. I'm doing my best. 4 carbons is butane. This is C4H10. So the first 4 hydrocarbons, their name has nothing to do with their structure because we thought that'd be a good idea. After butane, all of the names tell you how many carbons are in the molecule. Right, so that makes it way easier. So for all the straight chains after butane, next slide, right, 5 carbons. Go. 5 carbons is going to be pentane, right? Pent for 5. C5H12. Propane, butane. Can you see? Oh, I know what the problem is. Is that better? Sorry, I forgot that if I slide it over on my laptop, it cuts off the screen. My bad. Look, old man dealing with technology. This is great. You're like, I left my parents at home to not have to set, like, timers, and now look at me. All right, boop. Yeah, we're not going to fit another one on here, so we're going to go to the next page. Doop. 6 carbons. So we're gonna deal with this in a second, but the answer is yes, because I am a stupid chemistry robot, and when I see a bond that doesn't have anything on it, that actually reads as a CH3. And so if you don't have something on the end, I read it as a CH3. So you have to make sure you have something. There, this is hexane. C6H14. I've got to get better at repeating the questions for the YouTube videos. Okay. Next step is 7 carbons. Let's see, start for the hydrogen. So 7 carbons is heptane, C7H14. Boop. There's 16. Sorry, 16. My brain was off. 16, sorry. He's so old and just confused. Yeah, I was seeing if you were paying attention. Yeah, that's right. All right, next. I swear that one's an H. This is octane. C8H18. I've got to fit 2 more on here. This would be good. We're going to 10. Yeah. 7, 8, 9, 10. No, we're going to go to 9 first. This is nonane, C9H20. Yeah, so something that I'm gonna stress going forward, this is a good time to introduce it, is, right, the way you orient your chain doesn't impact what the molecule's name is, right? Because the name is just based on how many carbons there are. So it doesn't matter if I have it like this, or like this, or like this. It's all going to be the same thing. So it doesn't matter if it's up and down. If it looks like a swastika, that's just a little shady. It's got bigger issues. But it doesn't matter. It just matters how many carbons there are. And that's what gives it its name, not their orientation relative to one another. And then the last one, 2, 3, 4, 5, 6, 7, 8, 9, 10 is 10 carbons. We're going to hope they all fit. And that's going to be decane, C10H22. All right. So everything basically from ethane forward, right? Is part of a homologous series. And what that means is they only differ by the addition of a CH2. Right? So each atom or each molecule that I showed you, starting at ethane, the next one up in the sequence just had a CH2 stuffed in the middle of it. So I'm going to go back. Right, so you have ethane. The difference between ethane and propane is you just stick a CH2 in the middle of the molecule. So ethane and propane are part of a homologous series because they just increase by a CH2. Propane to butane, I add another CH2, right? So each of these just increases by a CH2. All right? What do you mean specifically? No. It has to be CH2. So like the homo prefix that gets used sometimes in like common names specifically means a CH2. So the members of a homologous series are called homologs. All right, so each one of these just goes up by a methylene, a CH2. This is... Go ahead. Inorganic, yeah. Yeah, inorganic. So there's like an allyl group, and then there's like a homoallyl group, and it just has an extra CH2 in it. All right, so that is the term. So here's the part where I threaten you. You have to know all of these, like the back of your hand. If next week I call you at 4 o'clock in the morning because my baby's got me up and I'm like, I don't want to be alone, and I say, what is the name of the thing with 7 carbons in it, the straight chain with 7 carbons, you have to say 2 things. Heptane and why are you calling me? All right? Those are the things that have to happen in that order. You have to know these. Because if you don't know these, you can't name anything. Right? The basis of all of the naming that we do is based on you knowing these 10 names. All right? And what they mean. When you hear octane, you're like, I need to draw 8 carbons in a straight line. And then I can go from there. But you have to know these. If you're like sitting at your house taking your exam going, methane, ethane, 3-ane, propane, you're never going to finish the exam, right? You just need to know these, okay? You just need to have them in your head. So, that was exceedingly painful, drawing all of those out, correct? I think the technical term is that... Okay, drawing hydrocarbons. That was awful, correct? We're never going to do that again. So we're going to do skeletal structures from now on. right? This is where we get into like peak organic, all right? So ethane, right? It's just two CH3s. This is that way of drawing it. Ethane, just a single line. Propane, right, versus propane. Right, so skeletal structures allow us to just not draw any of our hydrogens ever again. Right, so, right. So in skeletal structures, hydrogens, oops, change colors again. Are understood. We just know that they're there, right? So when we draw this, right, any line that ends the CH3. Right, so anytime there's a line that comes at the end of a chain, that is a CH3. Any bends, a bend is a CH2. So anytime there's a bend in your structure, that's a CH2. So this, and this are all CH2s. And this here at the end, over here is a CH3. So wherever the lines meet or end, that is a carbon. So this molecule has 1, 2, 3, 4, 5 carbons in it. This is pentane. So whenever anything ends or bends, you know what that is. So as we want to add more things, we have to take off hydrogens. So we good for me to switch over a slide? No one's flailing their arms. That's good. Thank you. Right, so this carbon right here, right, you can see 1, 2, 3 carbons that are bonded to that, right? How many bonds does carbon make? 4. So, if you can see that there are 1, 2, 3 carbons bonded to this carbon, that means this carbon only has space for one additional group. So we know that this has to be a CH, right? It has just space for one hydrogen on it because it's bonded to 1, 2, 3 carbons. The only other space we have is space for a hydrogen. So even though that hydrogen's not there, you can infer that it's there by seeing how many carbons are bonded to that carbon. Right, so if we were to do something like this, right, how many carbons are on that, how many hydrogens are on that carbon, on this carbon right here? 0. So this is just a C. There's no H's on it because I can see 1, 2, 3, 4 carbons bonded to it already. All right, so you can just kind of count how many carbons you have and know how many hydrogens should be on that carbon that you're interested in. What's that? Higher. Hexane. We have 1, 2, 3, 4, 5, 6. So you're never counting the lines, right? 1, 2, 3, 4, 5. Like, you don't count the lines, you count where the lines begin and end. What's this one? Nonane? 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so you should just be able to count where all your lines begin and end, and that'll let you know how many carbons you have. Seem reasonable? Okay. Oh, I'm going to still try to do this, like, with this whole Zoom lifestyle. I'm going to ask non-rhetorical questions. So far, you guys have picked up and answered them. But, like, if I say, like, hey, are we good? You can say no, and I will try again to the best of my ability. Or you can say yes and we can move on. But I don't want you to feel like you can't say something. So if you want to... Oh, hey. People are, like, killing the chat here. I've only got so much bandwidth right now. So you have to, like, give me a second. Again, if you watch the video, not a Twitch streamer, I can't work chat and, like, play the video game. So I'll do my best. All right. So let's see if I can add a slide now. So alkanes, which is what hydrocarbons are. Alkanes all have the same general formula. And you may have picked up on it when I was going over all the different hydrocarbons. Right? It's always going to be CN, so the number of carbons, and then the number of hydrogens is going to be H2N plus 2. So if you look at the structure of something like pentane, right, you can kind of see how this formula kind of comes to be. Let me get rid of that one for a second. Make them green. All right. So if you look at pentane, right, you have 3 carbons. For every carbon, right, you have 2 hydrogens. 1, 2, 3 sets of 2, right? And then at the end, you have 2 extra hydrogens, 1 on either end, to cap the chain. So the plus 2 are these 2 hydrogens at the end of the chain that kind of cap off and end the molecule. And then the H2N are the 2 H's on each carbon that goes through the chain. So you can just look and go like, okay, I have this many carbons, I have to have this many CH2s, and then an H on each end to cap it. Right? So what's nice is that for really simple molecules, their name also tells you their structure. Right? Oops. So methane, there's only one way that you can arrange a carbon and 4 hydrogens, right? That's like I have drawn here, right? So the formula and the name are going to tell you exactly the structure, right? So if I go over a slide, so if I do C2H6, right? There's only one way that you can put together C2H6. It has to be Fa, right? You can't do that any other way. Right? Same with propane. 3H8. There's only one way that you can put together propane. Right? Once you get past propane, your molecular formula does not tell you what the structure is, because past propane, you can start putting things together in different arrangements, in different orders. So, for example, so C4H10, right? I can put that together two different ways. So I'm going to do a skeletal structure. I can do that, right? CH3 on the end, a CH2 in the middle, right? Oops, it's awful. CH3, CH2, CH2. Right, and we count that up, 4 carbons, 3 and 3 is 6, 2 and 2 is 4, that's 10 hydrogens. So we're good. But I can also do this. So this is CH3, 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 and then I have an H in the middle, right? It's still 1, 2, 3, 4 carbons, 3, 6, 9, 10. It's still C4H10, but there's a different structure, right? The way the atoms are arranged is different. That makes sense? Everyone see that? We on board? A heavy sigh. Is that a... Sorry. That is a skill you'll have to develop, because once we do more stuff, I will use all the colors of the rainbow. In a regular semester, as he goes to his bag, I just throw piles of markers at the whiteboard and just do stuff. You won't get to live that life until hopefully the spring. Come on, vaccine. But you see how these two molecules have the same formula but look different, right? So these are called, get a good color here. These are called isomers. Right? So an isomer, kind of the simplest sense, same formula, different structure. So our example of this versus this, these are a more specific type of isomer called a constitutional isomer. Right? Where how the molecule is constituted, how it's put together is different, right? So here it's a CH3, gotta use something, a CH3, a CH2, a CH3, a CH2, and a CH3. Here it's CH3, CH, CH3, and then another CH3, right? So how the molecules put together is just fundamentally different, right? Score. All right. So constitutional isomers are also called structural isomers, which makes sense, right? They're isomers where the molecules have different structures. All right. So there are some common names of different units you see. I'm going to teach you these just so you know them. We'll use them a little bit in naming. So the first one is iso. As I always have the yellow pen up. So the question here was since there's an R group on the iso, if it is still a CH2 at the bend or if it's a CH. And so then I kind of go through an explanation, which was the R group still counts as something that's attached to that carbon. Sorry, you can only have 4 groups on that carbon. The R group counts as a group, so you end up with only having a CH at that yellow dot carbon. So we have iso, we have neo, which is this. So you have a carbon bonded to a CH3, bonded to a CH3, bonded to a CH3. You have a CH2, and then you have that R group that can be anything. So this is neo. The question here was, are these isomers of each other? No. So these are like names that we can give to different structures when we're naming isomers. So you have iso. So for example, this, where all 3 groups, all 3 carbons are in a straight line, this and then iso are different, even though they have 3 carbons. Does that make sense? Okay. Neo is, again, it's a name of like a subclass of structure. So this has 5 carbons, and it's like this. And then we have tert. This is one we use. Tert and iso are the ones we use the most. This is CH3, C, CH3, CH3R. So these are the 2 that get used the most, are tert and iso. And I'll show you, tert and iso. I'll show you why in a second. Okay. So this R. Sure. I've not done this thing live before, so I don't have the pacing down. So if I'm too fast, just let me know. Like I'm amenable to going slow, or not too slow though. We got places to go, people to see, molecules to draw. Oh, no problem. Okay, so how many carbons are in the box? 3. 1, 2, 3. So that's going to make this it's going to make it propyl, because it's 3 carbons, right? It's going to be like propane. Trust me, propyl for right now. So it's going to be isopropyl. So iso is telling us how the carbons in this propane are arranged. That makes sense? Same with tert, right? How many carbons are in the green box? 4. So that would make it, what's 4 carbons? We have butane. So this will be tert for the shape, and then butyl. I'll tell you where the YL comes from in a second. Don't worry about that right now. Right? But we use these a lot because tert, butyl, and isopropyl are structures that end up hanging off of molecules a lot. So those are the ones that we use a lot in naming that will come up pretty frequently. All right. So I've brought up naming a few times, and this is kind of going to end on this, which is just every compound needs to have a unique name. All right. So there are millions and millions of compounds, and so there are going to be millions and millions of names. It would be way too difficult if we just gave them all kind of common, non-systematic names, right? So, right, it's hard enough, let's be real, it's hard enough for you guys to learn all your professors' names, right? And you got like 5, right? At some point, you're going to like ask someone and be like, yeah, this tall guy is my lab instructor. They're going to be like, that's all you got for me is tall guy? And you'd be like, yeah, Dr. Tall Guy, right? So I can't expect you to just memorize a bunch of random names. So we've devised a systematic way of naming compounds, and that is the IUPAC system, right? So if you learn the rules for naming compounds, you can name any compound I give you by just applying those rules. So the next set of things we're going to do is we're going to focus on learning the IUPAC rules for how to name compounds. And once you do that, you'll be able to name any simple hydrocarbon that you're presented with. And we'll probably get through that Monday or Wednesday. So with that, I think we're done. The questions here were kind of about what order you should do the homework versus the reading in, and how to best approach the, I guess now, book smarts. It's book smart now? Oh man. It used to be LS? Okay, they changed it on me. The homework has been a journey, as I'm sure you all know. So I don't care. I think for the most part, the problems you can do just from lecture for the most part, and you don't need to go through and read the book. I'm not going to discourage you from reading the book, but if you're in a problem and you don't know how to do it, there's usually a link out to that part of the book. This first homework is all Gen Chem review because homie don't teach Gen Chem. So that way I would say read the book for that stuff if you're a little lost. But it's up to you. I don't think there's one way to do it that's better than the other. Sure. You too, bye. Thanks for coming. You too. It actually worked.